So just one announcement before we start, and that's that the bonus survey isn't up yet because it's a survey about unofficial St. Patrick's Day we do every year, and it's only open during unofficial. So it's just open for the 24-period hours starting Friday at midnight at 12 a.m. And it goes to 11:59 p.m. And you'll see why once you read it. So, but it also has some other interesting questions on it. One is about the strike, and other ones about school shootings and about how to protect against that. So, I think it's a interesting survey. And then there's a lot of fun stuff about unofficial. So you'll see that. So that's when it's open, and if you've been in Stat 100, you know about it. But we've added some new questions, some topical questions. Okay? And then the other thing that's due is Friday is an R bonus assignment. You don't have to do it if you don't want to, but it's a nice intro to R. And it doesn't take that long, and it's our second R bonus. That's due Friday at midnight as well. And the homework's posted, then after today's lecture, you'll be able to do the homework that's due Monday. All right, so chapter 17, we're interpreting the slopes in the multiple regression model, and we're going to try to do it graphically, and then we're going to try to picture them in 3D. That's the first thing we're going to do, just looking at what those slopes mean in the multiple regression equation. And then the last half of the hour, or the hour and 20 minutes, we're going to do inference on multiple regression. So we'll be doing the same F and chi-square tests in the same ANOVA table that we did before in chapter 11 on simple regression. We didn't have to do it for simple regression. We do have to do it for multiple regression. All right, so let's look at this. As we said before, that the slope for each predictor variable in the model controls for the other variable, right? Basically, what that means is that you're trying to compare apples to apples. So you're saying for people who are exactly the same on all the other variables, let's say you have even more than two variables, on all the other variables, the people, X predictors, they're exactly the same. How does that particular X change? How does it affect after you control for all the other variables in the model? So in the example that we're looking at, which was we were continuing with this idea of predicting finals, exam scores, it's taken from real data, predicting, I'll put a little hat over, our students' final exam scores from their homework, and we had this coefficient for homework, plus their exams. And we had some coefficient for exams, some slope for exams. This is from real data. And then we had an intercept term. Usually we put that at the beginning. I'm just writing it at the end here. So that is right down here too. It's just, that's what we're working with. So what I'm saying is that what this slope does right here for homework says that for those people who have the same exam scores, let's say they both have an 80 on the exams, this is the difference that an additional point of homework, just this fraction of it, 0.1641, how that on the average raises their final score. And you can, this coefficient from the exam says for people who have the exact same homework score, you can see it's a lot bigger effect that exams have on the final. So that's the idea. And we say that these slopes in the multiple regression equation, they're called partial slopes. We talked about that last time, and you did homework on that, since they quantify the effect of each variable after the other one is controlled for, partialed out or controlled for. So after that doesn't figure it anymore, how much extra information do we get from this variable after this one is accounted for, and vice versa. So it separates out those effects. Okay, that's what I said here. All right, so let's do this example here. And it says, example 1, find the 3 multiple regression equations for those with exam scores of 70, 80, and 90 by filling in these 3 blanks here. Okay, so this is so small for me to see right here, but it's saying exactly the same thing as up here, right? And now these 3 lines are for people who have the exam scores equal to 70, that's the lowest, exam scores equal to 80, and exam scores equal to 90. And then we're going to see what these equations are. Now, I just want you to see these parallel lines right here indicate what? They indicate, we're assuming that this homework has the same effect on people who have high exam scores as people who have low. Now, that's not necessarily true. The homework might help the people more who have low scores than they do high. Then we'd have to include an interaction term to account for unparalleled slopes. But multiple regression without an interaction term assumes, that's what I'm saying here, that you have that the variables have the variable has the same effect throughout the range of the other variables, okay? It's not necessarily true, so we're going to look at that next time, or later in the chapter here. All right, so now what are we going to do? Okay, so those for exams who have 90, we're just going to, what are we going to do? We'll just plug 90 in for exams right there. I can see it better up here. I'll just plug 90 in there and get an equation, okay? So I get 0.1641 times the homework. That's this little effect of the homework. This slight upswing that's the slope for that, plus 0.5824 times 90 for these people who have 90, plus the intercept. So those two together, when I did it, I got 64.326. So the equation is the final is equal to 0.1641 times the homework plus 64.326. So they're just going to have, they have the same slope. Each one has the same slope. They're just going to have different intercepts. Okay, and the intercept, there are 10-point differences here, so the intercepts will be just 10 points times 0.5824, which is 5. So the intercepts will just differ by 5.824. So this next one will be 5.824 less. You could do it out, and that's 58.502. And then another 5.824 less. If I plugged a 70 in for exams, and I got 52.678. So the intercepts are different. That's the idea. Sorry. Okay? So this is the multiple regression equation, and it stratifies. It allows you, right here, that's the multiple regression equation, and it allows you to stratify so you can compare people with the same exam scores. How much does the homework help them to improve on the final? Okay? Whereas the simple regression, and here's our simple regression equation, if you recall, the simple regression has a bigger slope. This right here, what I'm talking about is this slope for homework is bigger than in the multiple. And we saw that was true mathematically because you went from you derived the simple from the, by putting, substituting in for homework, or substituting in for exams, the relation between homework and exams. And you got a bigger slope here, and you can see that visually because they're correlated. Homework and exams are correlated. In other words, people with high exams also have, see their high, this is homework, and this is final. Okay? And because the people with the higher homeworks also tend to have higher exams. You get this simple regression. Here's the simple regression equation. It's this one right here that has a bigger slope. The simple regression estimates final exam scores, so it looks like it has a stronger effect because it's including the effect not just of the homework, but people with higher homeworks. As they have higher homeworks up here, they also have higher exams. So I just symbolized that, but more of them up here with higher exams. So that inflates the effect. If we were looking for a causal effect, this is confounding. The overall would be misleading. It would be confounded if we were talking about a causal effect here. Okay? And then when you include the exams in a multiple regression equation, it has the effect of stratifying, breaking the population into likes. So you can now look at everybody who has a 70 and you see everybody who has an 80 and everybody who has a 90 separately. That's the idea. So we should say that maybe the simple regression equation shows homework, this one, shows homework having a stronger effect. Having a stronger effect on final than it really does. Then it really does. And then when you compare like people who have the same exam scores, that slope gets much less. All right, that's the idea. Now we can do the same thing. Let's do the same thing here. Okay? Now we'll look at people, we'll see the effect of exams for people who have the same homeworks. All right? So the exam slope describes the effect of exams on final. When you look at this multiple regression here, this slope right here describes the effect on finals for those with the same homework scores. For those with the same homework scores, the predicted final score is what? It's going to be 0.5824 points higher for each additional increase in exam averages. All right, we can do the same thing here. We can say, okay, let's look at everybody who has a 70, for example, on the homework. What would their final be? Well, their final, they're all going to have this same slope, assuming there's no interaction, right? And it's just going to affect the intercept. And that slope, again, is less than in the simple regression. Remember, here's the simple regression down here. This is less for the same reason, because we separated out the effect, the two effects. We partialed it out. So it's only part of that slope. All right, so let's do it. So we have that plus, for people who have a homework of 70, we'll just plug 70 in there. So we get 1641 times 70 plus 11.91. All right, I did that. And the intercept here is 23.387. Now as you go up 10 points in the homework, you'll just go up 10 times that slope, which is 1.641. So you could add 1.641 to that. Or you could plug in 80 and it will be the same thing. So if you add 1.641 to that, you get 25.038. And here another, if you plug in 90 or add another 10 times 1.641, you'll get 26.679. So that's the idea. Any questions so far? Okay, so we're going to look at these equations and the three on the other side in 3D space in a minute. Let's just answer this question here, what we're on here. It says the equation for the simple, this went up from 0. The equation, why is the exam so smaller in the multiple? Look at the difference between those two. Why is it that way? And we can look at these 3 options here. And do you know which one it is? I should have done this as an iClicker. I'm curious what people think. Why don't we just call this A, B, and C and take out your iClickers, because I didn't write it as an iClicker, but let's just go to the iClicker. And you'll choose either A, B, or C. I just want to know what people would think. So I'll start the iClicker on that. And choose on page, for those of you at home, we're on page 88, and choose either A, B, or C. It's part D on page 88. Okay, I'll just let it go for a minute. Just 5 more seconds and then we'll stop it. Okay, everybody had a chance to vote. And let's stop it. And the answer is B. And let's see if you got that. Great. It's not an easy question. Great. I guess it's because you just did that homework on it. That's terrific. I'm really happy about that. Okay. All right, let's go back to the document camera now. And so the answer is B. Because there's a positive correlation between all of those. And the effect of homework is combined with exams. This is not only including the effect of exams, but it's including the part, also that part of homework. Remember, those two things are correlated, and you can't separate them out. So this is larger here. If they were no correlation, then they'd be the same. Okay? In the simple and the multiple. All right, now let's move on. And all right, so we saw that it assumed that so far we've assumed that unless we had an interaction term, we have these parallel slopes, right? So multiple regression assumes that each predictor matters just the same amount, regardless of what the values of the other predictors have. It assumes the slope of each predictor is the same for all values. But often that's not true. For example, doing the homework may make more of a difference in raising final scores for those who have low exam scores than those who have high. In that case, we'd have to add an interaction term. And the basic picture is the same as we already looked at before. Here would be an interaction term. Like let's say these top-heavy little pyramids indicate high exam scores and the bottom are low exam scores, let's say. And here is uncorrelated predictors, right, and no interaction. Here's correlated predictors, right, but no interaction. And here is an interaction, but no correlation. If we talk about correlated confounders in a causal way, that's correlated predict. I really don't want to confuse you. This is a very hard picture to understand. So I want you to just relax. And this particular picture is we're not going over it long enough for you to be tested on. So I don't want you, I would spend more time on it if I'm going to put it on the exam. And so far there isn't homework on this particular picture. I just wanted to describe it to you. So if I go over it a little bit quickly or not a little, don't worry about it, all right? Since it's here and since we had a very similar picture, the way you can think about it is that these correlated predictors, if we're talking about a causal interpretation, there would be confounders. And so if we want to think about it that way, here you have parallel slopes, so you have no interaction. You only have confounding, so this would be no interaction, only confounding. Here would be neither interaction or confounding. This would be only an interaction. What would both look like? I better draw both so you can see. Both would look like something like what? You'd have unequal, let's say the homework, those with low homework, it had a positive effect on finals. So this is finals, this is what we're doing, this is homework. And these are the people with the low, so I'll make a triangles bottom heavy for low exam scores. So these are people with low exam scores. Okay, so the homework has a pretty strong effect on them. Now if it was an interaction, I have to do a different slope for people with higher, okay, so it would be a difference, it would look like this, right? So it would look, why don't I make a sort of almost flat slope up here for the people who have the higher exam scores. It would look like this. This would be both. Confounding. So this would be both. But I know it's a little confusing and it's pretty, so don't worry about it for now, okay? Just read the text here. This is important. And we've talked about that. All right, so let's move on now, and let's not lose our train of thought. So I want us to remember what we're doing here. And what I said I would show you is these three, whoops. Got to readjust here. Okay, I said I would show you these three parallel lines here, and these three that we see squashed into 2D. I'm going to have you visualize them in squashed into 2D here in the way they really look in 3D. So let's move to page, we already did page 91. Let's move to page 92. All right. And here's our multiple regression equation right here set in, and it's the equation of a plane. And you can see that plane right here. All right? And this slope right here, you see it's a bigger one. This is the tilt going this direction. This is the tilt going, so this is the effect, this is exams, and this smaller tilt is the effect of homework. All right? So the smaller tilt, let's see, so this is, you look down here, this is homework, right? So this is this line right here. So this is the homework going this way, right? So for everybody who has a homework of 100, see how this would be the effect of exams. We want everybody who has a homework of, what, 90? So this is homework of 90. This is homework of 80. See, this slight slope up is the homework because it only has a slight slope. So these three lines indicate, but the steep is the effect of exams have for these three groups. So these three lines right here, you see, can be expressed by the three equations we just looked at on page 88. That was the first, right? So these are the three parallel lines for the different homework scores. Which one was that? Let's look. On page 88. Does that make sense to everybody? And now this right here is the small effect. So this had the big effect here. Now let's look at our different exam scores. And our different exam scores are going to be an exam of 90 way up here, and an exam of, so this is an exam score of 90, this is 80, and this is 70. And you see how these lines have the more gradual slope, right? So that is going to be when we had, they all had this gradual slope of 1641, and that's these three lines. See how they have the gradual slope here for exam scores of 90, 80, and 70. This is what they look like in the plane. So these are exams right here. This right here is exams. And these are the three parallel lines on page 87. Those are the first ones we did. Okay. Does that help you visualize it? Can you see this plane here? Some people can see it. Can you see a plane there? And you know that 3 points determine a plane. So we have, this is the equation for a plane. And these lines up here, like some of these like have a big positive error and some of them have a big negative error. We're going to be, this is, you know, with most of our multiple regression equations, we're going to be having more than two predictors. So we're not going to even be able to visualize it. After we leave 3D space, we won't be able to visualize it. But I figured you might as well try to get a feel for it right now. Yes?
Are the lines coming from the bottom of the graph, from the zero plane, or is it coming from the plane of the function?
These lines that we're looking at are, the vertical ones are coming from the bottom. They're coming from these, the vertical ones are coming, yeah, from the bottom, and they're going up high. I used R to draw this. So that's one of the bonus problems, I think, is making 3D plots in R. Okay. Now our assumptions. These assumptions we already, why are we talking about assumptions? In order to make inferences. So far we haven't made any inferences. But let's say we wanted to make inferences to a wider population, extrapolate to a wider population. Then we need to make some assumptions, just like we did for simple regression. And they're the same assumptions. They're the same exact ones that we looked at back in chapter 9. And what were they? The data has to be modeled as some kind of random sample from a larger population, if we're going to make inferences about a larger population. So, or if we want to make, there's another way we can think about it, or is coming from a randomized experiment. And we're going to look at another way of thinking about it when we do something called re-randomization techniques later in this, in part 5. All right. So each of the predictor variables has a linear relationship with the response variables. And then to use these standard, this is to make inferences, to use these standard statistical tests, like that are basically the ones based on the normal curve, like the F and chi-square tests, we have to make this other assumption that our errors are independent, roughly normally distributed, and have with equal variance. And it's often written as this: they're independent, the errors are independent, identically distributed, normal, with mean 0, and the same variance of sigma. Okay? So these are exactly the same ones that held true before. So let's check these assumptions in our example. We'd have to say the 107 students were randomly chosen from a large population of 2,000 students. 2,000 or bigger. That's what our example pretends. They really weren't, but we're pretending that. Let's assume it. If we don't want to assume it, we can do something different. I'll show you what we can do, but for now, let's just assume it. All right? The plots for homework versus final and homework versus exams versus final both show a linear trend. We checked that. Remember, we did that already. I showed you the two. Where were they? Right here. That was back here. And then we can only check these last assumption, the distribution of the errors, after we do the analysis and plot the residuals, right? So we'll examine how to check this assumption after we do a significance test for the overall model in the next chapter. That's in the next chapter. That's what we're going to do. And so we're going to be checking these assumptions throughout the course, but what should we do if they're violated? And they're always somewhat violated, unless you have a made-up example, pretty much. And that's not true, but usually in most real-life cases, they're somewhat violated. So what if random sampling is violated? It actually was in this case. This happens all the time. We try to assess how closely your sample reflects the population. For example, let's say your sample's all college students. You're not going to make inference about all adults, right? You wouldn't do that. We'll talk about this more. Linearity violated, that's going to be our section on we're going to try nonlinear functions, curvilinear functions. Either do that or transform the data to make it look more linear. And that we're going to do in part 7, transformations of data. And if the errors, what if they don't have equal variance? Then you do these data transformations. In part 7, we're going to look at which ones help in making the errors more normally distributed, more equal variance, and these non-parametric methods that we're going to do in part 9. These are fun to do, different non-parametric methods that don't depend on these assumptions. I think you'll like them. And finally, what if the errors aren't normal? Well, then there's a lot we can do. We can use these re-randomization methods that we're going to do in chapter 22. We can do data transformations or non-parametric methods. There's a lot we can do. So, but that's to come. Right now, let's just say the assumptions are okay. And we're just going to use our usual F and chi-square tests. So, and there's nothing new to learn here because we've already done it with simple regression. There's really nothing new to learn, except the only thing new is the degrees of freedom are going to change because we have an extra parameter. Now, we have another x variable. That's all that's going to change. Okay, so testing how well our sample regression equation fits the population regression. Okay? So, we found this equation where these sample betas, these sample slopes, gave the best least squares fit. They minimized the sum of the squared errors in what we were trying to predict, finals, for our particular sample. But before we go any further, we want to check whether we think those slopes accurately reflect the true population slopes, and we call those the Greek letter betas, we'd get for the whole population. You see, the problem is maybe they're just fitting some accidental features of our random sample. Maybe the null, just the really strict null, that all those betas are 0, that there's nothing to our model, that they're all equal to 0. We might as well just, if they're all equal to 0, we'd only have an intercept term, and that intercept term would be the average of all the finals. Maybe the average of all the finals works just as well. Okay, would be good within random, typical jitter. Okay, so now that we have more than one slope, our first step is to test whether any of the slopes in the model are significant. That's not an intentional big space there. Just the typesetter did that. Okay. Okay, so it's called the overall regression, to see if there's anything in your model. This is the first step, the you're just looking at the collective effect of all the slopes together and to see if there's any overall regression effect, all right? And the null hypothesis then is that all the betas are equal to 0, except for this one. Okay, that all these slope betas are equal to 0. And that's the same thing as saying that the multiple correlation coefficient is 0. And it's also the same thing as saying that our best prediction for y is just the average of y's. And the alternative hypothesis is at least one of the slopes is not 0. At least one of them is not 0. That's the same as saying r squared is not 0. It's the same as saying at least one of them means any one of them or any combination or all of them, or if we just have two of them, either one or both of them. Okay, so now okay, with simple regression, we had the choice, right? We didn't have to use an f-test or a chi-squared test. We could have used a z or a t. But now we have to with multiple regression. Why? And the key is because we just can't boil that difference down between what we observe and what we expect into a single-signed number. With two or more slopes, we have to look at two or more differences. Some could be positive and others could be negative, right? So we can't just sum them up the way we did. That's what we do when we do a z-test. We're just summing them up. Or with it, we're just saying the observed minus the expected. Instead, we have to square the differences before summing them up. So both the chi-square and the f-tests are based on comparing the sum of square differences. They're looking at variances, the ratio of variances, the sum of square differences. Okay? And as usual, as the sample size, if the sample size get large enough, as n goes to infinity, what happens? The f gets closer and closer to the what? As n goes to infinity, what do you think the f gets closer and closer to? The chi-squared. Same as when n, it's analogous to the t and the z. As n goes to infinity, the t got closer and closer to the normal curve, to the z. It converges. All right. So it makes bigger your sample size, the less difference it makes to use the t compared to the z and use the f compared to the chi-squared. You'll see that. All right. So same idea, and now let's just start with the chi-square test because it's so simple. Just like the z is so simple, the chi-squared is super simple. So let's do that. All right. So we found this sample regression equation is the best fit for our sample of n equals 107 chosen from a much larger population. And we got this r. Let's round it because this is too many digits. Let's round it like to approximately 0.62. Let's just use this. It's easier. All right. But does it fit the population better than the null hypothesis that all the slopes, homework slope and exam slopes, are 0? Right? The null says that knowing someone's exam score and or their homework average, their exam and homework average, is no help at all in predicting their final score. Common sense tells us to reject that null. Let's just make sure statistics agrees. Okay? That's all we're doing. We know to reject that null from common sense. There'd be something wrong with my homework and exams if they had no predictive value in determining what someone's final was. That would mean it just doesn't matter how you do the rest of the course. That doesn't make sense. Okay? But we're just going to do this test anyways. All right? So remember, this is the chi-square statistic. It's this r squared over 1 minus r squared times n, right? We used it for simple regression. We're going to use it here. Okay? We can use it. All we have to do is change the degrees of freedom. So let's do it. So what is this? This is going to be 0.62 squared, that's r squared. This is super easy, over 1 minus 0.62 squared times what? 107. And that's it. Okay? And I did that, and I got 66.81 as my chi-square statistic. Now, we talked about how the f, the mean of the f, is 1. So if you saw this as an f statistic, you'd say, whoa, this is so far out, such an extreme value, we'd have to reject the null. Well, I should probably tell you now that for the chi-squared, where can I write this? Somewhere. Let's just write it at the top. So a big note here, and we'll talk about it later, but I just want to over. As soon as I see this, I know this is an immense chi-squared. And it agrees with common sense. Tells us to overwhelmingly reject the null. And how do I know that? Because when the null is true, the mean chi-square statistic, it's not equal to 1, but it's equal to its degrees of freedom. Is equal to the degrees of freedom. And the degrees of freedom, remember, is p minus 1. And in this case, the degrees of freedom is p minus 1. How many parameters are in our model, including p minus 1? So how many, what do you think it is? What is p? How many parameters are in our model? There's 1, 2, it's the number of slopes including the intercepts. So it's 1, 2, 3. And p minus 1 in this case is equal to what? Yeah, p minus 1 is equal to 3 minus 1, which is equal to 2. So that's equal to 2. So I would expect a 2, and look what I've got here. All right, so let's just say, just so you remember, 1, 2, 3 parameters. Always include that intercept, okay? Those are the number of parameters. So parameters equals to 3. The degrees of freedom is actually just equal to the number of slopes because you subtract that 1 off. All right? So the degrees of freedom is just the number of slopes. Okay. So we know that's crazy, but let's just look how to read a chi-square table. So, and let's look at the critical values. But when you see this, you just know that's just over, it's way, way out there because we'd expect 2 and we've got that. Under the null, the chi-square statistic follows a chi-square distribution with p minus 1 degrees of freedom. All right? So we can find the p-value. The p-value stands for probability, not parameters here. P-value, right? So we can find the p-value by looking at the critical values, those cutoffs for various p-values on the chi-square table. Okay? Now, do you remember how to read a chi-square table here? So I just copied a little piece of it. It only has 1 set of degrees of freedom, and we know we're just looking at degrees of freedom 2. So that's where you should be looking. Right there. Okay? And now these are cutoff values here. So it says, how big a chi-square, what's the critical value? To reject the null at 5%. That's alpha equals, so here's 5%. Alpha equals 0.05. So we would need 5.99. So what that means is that on the chi-square curve with 2 degrees of freedom, just 5% of it is to the right of 5.99. How about at 1%? Well, then we'd have to go out further. At 1%, anything bigger than 9.21 would reject the null, because that's 1% of the curve is going to be to the right of 9.21. And how about at 0.1%? Well, then it's 13.82 is the critical value. So basically, it looks like if you wanted to make a curve, I'll draw another one. And that would, let's say that it looked like that. Then you'd say, all right, at 5.99, from here on in would be 5%. Okay? But then at 9.21, here on in would be 1%. And then 13.82 would only be 0.1%. Does that make, do you understand? Yes. Oh, good question. No, like if we were dealing, her question was, aren't we going to have to divide alpha by 2? Because if it was 5%, wouldn't it be 5% on one side and 5% on the other? But remember, this is a chi-squared, and it can only be positive. Because the squared is not going, it's only going to be in this direction. We're only looking at the right-hand tail because chi-squared could only be positive. Okay? So we don't have to do that at all. So we just look at the right-hand tail. Any other questions? All right. So let's do an eye clicker now for your conclusion here. So let's, for part of the conclusion, so let's go to the eye clickers. And so this is just part 4. I'm saying, what do you conclude? Like, compare our chi-square stat of 66.81. It's way far out there to those critical values that we just looked at in part 3. Those critical values were what? 5.99, 9.21, and 13.82. So what do you conclude that our p-value is? Where do you think it is? A, B, C, D, or E? Okay, can we stop this? Is everybody done? Oh, yeah. All right. And so the answer is D. Good. Most people got that. All right. And let's look. Okay. So the p-value is less than 0.1%. Because our chi-squared of 66.8 is much bigger than the chi-square critical value of 13.82. That was the cutoff to reject the null at 0.1%. So, just curious what this next clicker question is. Okay, so what do you conclude here? Let's start this again. So what do you conclude? Remember what the null was. It was that all those slopes were equal to 0. Equal to 0. All right, I'm going to stop it at 1 minute. So just to answer. Okay, so it's C is the answer. Let's see how many people chose that. It was between A. Okay, I can understand why you chose that. All right, let's look at let's think about it a little more. All right, what do you conclude? Reject the null and conclude either one of the slopes or both of them are significant. Remember, the null is that all the slopes are equal to 0. So rejecting the null means that not all the slopes are equal to 0. Rejecting that means that at least one of them, the null is that every single one of them is equal to 0. So saying that's not true means at least one of them is equal. You know, they can all be, just at least one of them is not equal to 0. They don't have to all not be equal to 0. Does that make sense to everyone? Do you understand? Okay, so let's write that on the document camera. And, okay, so what do we have here? So first of all, what did we do? So we looked at that. 13.82 was out here. It was up here. 13.82. Sorry, so hard to read, but beyond that was 1%. But ours was 66. It's way off. Ours is 66. It's way off the page, so it's much less than a probability. When the null is true, only 0.1% of the time will we see a chi-square statistic bigger than 13.82. So this little probability, the area to the right of this, is just 0.1%. Ours is 66.81, so it's way, way off. It's almost 0, the probability. But first, let's just write down what we concluded just looking at that. So what we did was we said we compared our chi-square statistic of 66.8 we compared that to what? And we saw that it was much greater than the critical value of chi-squared. The critical, put a little star, this means with 2 degrees of freedom, and that was equal to 13.82. All right? So it was much greater than that. And this was what? Alpha equals 0.1. So this was at alpha equals 0.1%. We usually write it alpha equals 0.001. Okay, that's what we did when we looked there. That's our critical value, 2 degrees of freedom at alpha, that's alpha equal to 0.01. We did that, and we saw it's much bigger, so it's further out. So our p-value, has to be less than 0.1%. It's really, really small. It's almost 0. And if you actually had a calculator, then do you want me to do it on the computer so you can see what the actual p-value is? Do you want me to do that? Raise your hand if you do. Okay, let's do it. It's fun. All right, so let's just do that. And I bet it's going to be tiny, tiny. And so let's get rid of this. Escape. And get down here. And pull up our p-value calculator. Okay, so we're on a chi-square distribution. We have 2 degrees of freedom. And we have a chi-square statistic of 66.81. Let's see what we get. So we're going to compute the p. Oh my goodness, look at that. I told you. It's really, really, really. Chi-squared is out of the plotting range. That's what it is. How many zeros is that? 1, 2, 3, 4, 5, 6, 7. Okay, it's we can write it down. Let's write it down. Okay, just for fun. So we actually can get the real p-value. This is so huge. Remember we said it was so huge, we knew it was going to be our actual p-value for chi-squared equal to 66.81 with 2 degrees of freedom is 0. And we had like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We had 12, but I'm going to change this into a percent. And then what was the,
3107?
it was, we can look. I just go. It was, yeah, 3-1. Okay, let's go back. 3.1%. So it's basically, on an exam, like if you say, you could just say it's almost 0. And I want you to get a feel for that. I mean, because the mean, the average, as we can see, we can go, I can show you that, is, I said, was 2 because they have 2 degrees of freedom. So let's look at that. So the average chi-square statistic would be 2. Now that's not going to get us 50%. It's only going to give us 36.79%. Why? Because it's not the median. The median is the 50% point. Remember? So the with a long right-hand tail like this, the average is greater than the median. So the median, the 50% mark, would be more like here. The average is 2. It's greater than the median. Okay? Well, that's pretty neat. Now, I just said there was no left-hand tail, so what is this left-hand tail doing here? What is the left-hand tail doing? That is, when would you ever use that? You know when you use it, it's like when people would say something like, oh, they fake their data, and they'd say, oh, I got a chi-square of like 0.1 or something. And then you compute the p-value for the left-hand tail, and it's less than 5%. You think they're faking their data. Because people have a very bad sense of what would just happen due to random chance. So they think, oh, you'd expect 0 if the null is true. No difference from that. So it's to check if people are faking their data. All right, let's go back to the document camera. And now let's do the F test, okay? We're going to do the same thing, but now we're going to use the F. Okay, so that's what we're going to do now. So the F, do you remember the F? Okay, the key part of both is this, but what is the difference? Okay, so here's our chi-squared right here, and it's r squared over 1 minus r squared. And this n is really dividing these errors here. This is the strength of the errors, and each little point contributes an error. You know how it says actual minus its predicted? So you have n of those. So we're averaging those. But this n right here then appears in the numerator when we simplify. Now, when we do an F, we have this 1 minus r squared, but we make that usual adjustment. And instead of doing n, we don't divide by n, we divide by n minus 1 if you're doing a mean, n minus the number of parameters is what it always is. So in this case, we have 3 parameters, so it's going to be n minus 3. So instead of 107, this will be 104. That's just that slight adjustment we always make. Now, F has degrees of freedom here, 2. It has 2 sets of degrees of freedom. And in the model depends on how many parameters are in the model. This is the strength of the model. So you divide by the number of parameters in the model minus 1. You always subtract off that intercept. So this, why don't I make it a different color, is for the numerator, degrees of freedom. And this does not appear in the statistic, it just appears in the degrees of freedom here for chi-squared. You don't see this anywhere in the statistic, right? It's arbitrary that it's there. We really don't need it. But Fisher put it in to make the F statistic mean be 1, which I love. And it's gorgeous. I think that's great to have it 1. The guy who invented chi-square, a different guy, didn't put it in. So that's why it's not there. Okay, Fisher, and this was a guy named Pearson. We can look at that later. But this has this p minus 1 here. And we don't have it. So where does that end up when we simplify? It ends up in the denominator. And this ends up in the numerator, making things really confusing, right? That makes them confusing. But this right here is always the degrees of freedom for the f for your numerator, like we talked about. And this right here is the degrees of freedom for the denominator. And they get switched here when you simplify, but don't worry about that. Okay, maybe we should make a note of that. Oh, let's just make a note of that. Okay, so we'll make a note of this here, like these, just so you don't get confused. Say note when the f is simplified, when the f ratio, that's what it's called, the f statistic, f ratio, I'll just call it the f stat, is simplified. And I don't want you to get confused by this. The degrees of freedom in the numerator and the denominator get switched, but they appear in a switched way. This is still the numerator. It's just, okay? So just think of it, the numerator is always the p minus 1. And the errors have an n in it. All right, so now let's compute the f, now that you see all that. Okay, so the f, it's going to be the same thing we did before. So we have r, you probably forget what r squared, what r was. So we had, all we need to know is what? That r was equal to 0.62 and n is equal to 107, right? And we have to know the number of parameters was equal to 3, because we had 3 parameters in our model. All right, now know that, and so we have 0.62 squared, r squared, over 1 minus r squared. This is the same thing we just did. But instead of multiplying by 107, if we stop there, that's the chi-square. Stop there, that's the chi-square. But now we have to make that little adjustment. So we subtract off the number of parameters. So we end up with 104 there. And then we make an adjustment that's meaningless. It's just a convention, but you've got to do it because that's how the tables are. And it's, you take, instead of just leaving that blank, we divide by the number p minus 1. Okay, so this is 0.62 squared over 1 minus 0.62 squared, and then you just have this ratio of n minus p over p minus 1. Okay? And because of this, if we didn't have this, they'd be super close. And as n got bigger, they'd look super close. But we have this down here, so it makes them look really different. And remember, other one was 66 points, and this is going to be like 32, half of it, 32.47. It's too bad because that's why people don't realize they're really the same. People get so confused about this because they look different. All right, so how many degrees of freedom in the numerator? In the numerator, remember, the numerator, even though it looks there in the denominator, is p minus 1. So it's going to be p minus 1, 3 minus 1, so that's 2. And the denominator will be n minus p. That's 107 minus 3. That's 104. And that's 3 minus 1. Let's color them so we know. This comes from the numerator, and this is the denominator. All right, now we're going to do the same thing, find the critical value for f at the 5% significance level. Now, because we have 2 sets of degrees of freedom, here's the denominator, here's the numerator one. We have 2 sets. We can't have we can't show all the different significance levels. So this is just for p equals 5%. That's the same as alpha equals 0.05. That's what we have. All right, so what should we do here? So we have to look. Our degrees of freedom numerator are 2, right? That's this one is 2. And then in the denominator, we have 104, but that's not even appearing there. So that's, they call them, you know what they also call them? Degrees of freedom 1 and 2. So the denominator is also called 2, and our degrees of freedom in the numerator is also called 1. That's another way of saying it. All right, so that's 2. All right, so we've got that, and we've got this. Now, most people do this conservative estimate. Remember, this is based on your sample size, and they say, okay, we're going to do this conservative. So most people would choose this, but really it's going to be between these two, right? It's going to be between those two. So I want to show you them. It'll be between them. All right? And so most people typically they use the smaller one. So unless otherwise told to be conservative, if it's between two, use the smaller one. So we can do that if you want. But basically, how would you find this if you wanted to really find it? Because what we want to do is compare what? We want to compare our F ratio, our F stat, to the critical value for 2 degrees of freedom in the numerator and 104 in the denominator. And if we wanted to do it at alpha equals 0.05, let's say we wanted to do it at alpha equals 0. How would we do it? We'd go to the, let me show you how you would do it. You would go to here, and you would say this. Okay, we're going to the F. 2 degrees of freedom in the numerator. In the denominator, we have 104. And if we wanted a p-value, we want to find the critical value, we'd say we want the critical value of p. We'd have to compute an F for the critical value of that. And there, so the critical value is 3.084. So that's between those two. Let's write that down. So that would be equal to 3.084 at alpha equals 0.05. So we'd be comparing our, since 32.14 is much bigger than 3.084, you would say the p-value has to be less than 5%. It's going to be about 0, but do you think it's going to be bigger? It is going to be bigger than what we got with the F, but just by let's check it out. So remember, where should I see this? Note, when the null is true, F, the mean of the F, when the null is true, F's mean, the mean of the F stat, is equal to 1. Ours is 32.14. So it's going to be, this is going to be, our real p-value is going to be really, really little. Okay? So F equal to 32.14 is going to have a p-value almost 0. Let's see what it has. F equal to 32.14 when it's usually about 1. So let's look and see what it has. So we do 32. Oh, no, so we keep that the same, that the same. Here's where we say 32.14, correct? Is that what I came up? Oh, 0.47. Why did I write 14? 0.47. Isn't that, didn't we come up with 32.47? I have no idea why I said 14. 32.47. So let's see. How many zeros? 1, 2, 3, 4, 5, 6, 7, 8. Oh, so it's only 8 zeros instead of like as a percent instead of. So it is 1106. So it's, yeah, it's bigger, but you can't even see it. It's so far out there. It's essentially 0. So we can go back to the document camera and write that. We can say when the null is true, F is equal to 1, and 32.47, I'm very sorry about that, is so much bigger than 1. And where can I say the real p-value? Can I do this? Do you mind? So P, I just want to show you. So P was equal to what? 8 zeros, so 0.1, 2, 3, 4, 5, 6, 7, 8, and then it was 1106%. Now that's bigger. It's bigger, isn't it? Because the other one had 10 zeros. All right, so let's make a note of that. So we are going to reject the null, right? Aren't we going to reject the null? Reject null. It's the same conclusion we got with the chi-squared. And let's write that down here. Let's see what we want to say. Okay, so this is actually super interesting. I know it's the end of the hour, and I'm wondering what, can we save this for next time so I can just do an ANOVA table for you so you can do your homework? Okay? We can just say right here about the fatter tails. You should know this, the fatter tails, F and T, have fatter tails, okay? Fat tails. They have fatter tails. F and T have fatter tails than their respective chi-squares and z. So fatter tails means that the F p-value, the p-value using F, is fatter. It's bigger than the chi-square p-value, and it was. They're both almost zero, but it was bigger. All right. Now we're going to talk about why they're different. This is super interesting, but first let's fill out an ANOVA table so you can do your homework. And it's not hard to do this. Okay, so we're going to fill out this ANOVA table, and you know how to do this already. I know it's long, right? But what do we need to fill out this ANOVA table? First of all, we need the sum of squares, total, right? And I gave you the standard deviation of the finals. And so you can, and you need n. Remember the sum of squares total? Do you remember this is equal to n times the standard deviation of the y squared? So that's going to be equal to n times 10.27 squared. And I did that, and I got 11,285.6. So that's what goes in here. So this is another way to, this is like the, you can also do the F-test by setting up this ANOVA table, just like we did before. I just want to show you it's the same thing. Now, how are we going to find this, and how are you even going to remember it? Remember, just go back to our whole thing. See, I just want you to have this picture. You have this data, all these y's, and you want to break it into two parts. That's all we're doing, a model and error. That's all we're doing. And the data is this is described in the y's as the sum of squares total, the spread of the y's. The spread of the y's, the variability of the y's, is equal to what? Well, we're going to break this SST into the part r squared. That's the proportion due to the model. And here's the proportion, 1 minus r squared, due to the error. Okay? So now that we have this, r squared, remember r is equal to, let's just change this to 0.62 up there, okay? So we'll just do that. So we'll say 0.62 times 11,285.6 plus 1 minus 0.62 squared times 11,285.6. And when I did that, I got 4,338.18 here. And this one is 6947.42. Okay, so that's what we're doing. So let's just fill that in here. Okay, this is r squared times SST, and this is 1 minus r squared times SST. So we can fill that in. So this is 4,338.18. Sorry that I'm running over. I'm just going to run over like probably a minute. And that's 6,000. I'm just copying that down. Okay, now the degrees of freedom, do you remember what it is? N minus 1 is for the total, so that's going to be what? N is 107, so we'll have 106 here. And now we know it's p minus 1, and our parameters, it's the same problem. So our parameters are equal to 3, so we have 2 here and n minus p here. Remember, we just did that. They add up, 2 plus 1, okay? And what we do to get these mean squares is we just divide them. So we'd say that divided by that, and that divided by that. So this divided by this is 2169.09, and here I got 66.8. And that's our F statistic is just the ratio of those two. So it's really the same thing, 66.8. Okay? And if you have to, like, I'm not sure on your homework if you have to or not, but if they ask you for the standard deviation of plus of the errors, what would that be? That would be the square root of the mean square, the root mean square of the errors. That's equal to the SD plus of the errors. Okay, it's the same thing we did before. When we do this, we should get the same answer, 32.41 that we got before. And the reason we get the same answer, you can see really well, because F is equal to mean square model over mean square error, right? So that's R squared times SST for the model divided by its degrees of freedom over 1 minus R squared times SST divided by its degrees of freedom. And when we simplify that, we just get R squared over 1 minus R squared times N minus P over P minus 1. So it's the same thing we've been doing. All right, and we'll talk more next time, and so now you can do your homework. And yep, we went to the very end.